Okay, we're going to go on with the material. Can you see my full screen, Giovanna? Giovanna, can you see my full screen? Okay, so this is chapter 4. And as I explained you before, we're going to study uncoupled roll motion. It's a oversimplification, right? Because usually, as we said before, I mean, it's you don't have uncoupled motions. We have everything coupled. Even, for example, if you receive the waves on the beam, right? You go up. And even though you receive absolutely waves from the beam, right? The action on the fore and on the aft ends is different. So you're gonna have roll, heave, some pitch. And not only that, but it pushes you in the y direction. So you have some sway and you rotate a little bit because the effect on the forward and aft end is not the same. But it's quite typical, right, to study this problem independently, okay? So today we're going to deduce the equation of motion. Then we are going to say a couple of words about the added inertia. In this case, the added inertia is very complex, okay? And damping is even more complex. In this case, the damping includes the very viscous effects, okay? We're gonna do this using a method. It's an empirical method. So the Japanese people collected a lot of information, lots and lots and lots, and they developed some formulations to estimate the roll damping. And then the other term, it's in 4.3, is the excitation. So we're going to do a very simple expression to estimate the excitation. It's a very simple, it's you can find it in very simple books, but it's not inadequate. And then once we have everything, we can calculate the response, okay? So that's the general content of this chapter. So pure roll. So there is only roll, no other motion. So this is the situation, okay? And we're going to consider that we have an axis passing through the center of gravity of the ship. And we're going to take moments with respect to that point. Clearly, what is stating that here, okay? Since we are taking moments with respect to the center of gravity, the other term here, minus rho, cross, C cross RP double dot M is not here, okay, because rho C would be 0. This is the inertia, dry inertia with respect to this point. Okay, so we take pieces, and we take the distance to the center of gravity, and then we sum up, and this is the value that we have. Now here, we have the hydrodynamic force, okay, and this hydrodynamic force with respect to this point generates moment, okay? Once you incline, you know that the center of buoyancy moves in this direction. So we have this vector pointing in the vertical direction, and if the angle is small, it crosses the center line at this metacenter, okay? Since we are going to assume that the amplitudes are small, okay, this vector is equal to that vector. So we have no vertical acceleration, okay? So these are simplifications that comes with this problem. So we integrated this hydrodynamic effects, and we have the added inertia. We have the damping. I insist here is that the damping is a very complex situation, okay? Especially in raw. And the damping, okay, easily can become a nonlinear factor. The constant of the damping, if you increase a little bit the velocity, it will not be a constant anymore. So it will depend on the velocity. In general, we're going to linearize, but it's a good idea that you have this in your mind, okay? This is the restoring effect. So we have GZ, and that's this force, which is equal to that one. Okay, so this couple produces this moment. You see that it has gone in this direction, and this is the restoring, which points in the opposite direction. We need a negative here. And of course, we have the incoming waves generating a moment here, and we assume that it is harmonic. These are not in equilibrium, and they will produce a rotational acceleration. Okay? We have here, 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 and here we have theta. So we put all of this on one side, and everything else on the right-hand side, that's the excitation. So we have dry, added, times acceleration, damping. Oh, here there is an error. I need a bit a theta dot here. And instead of GC depends on theta. We're going to linearize that in a minute. And on the right-hand side, we have the excitation. You see that the excitation does not depend on theta, which is the angle of rho, okay? If we were doing a more general ship dynamics analysis, in that case, instead of theta, we would use eta 4, okay? But since this is just one uncoupled problem, this is the way we call it, okay? So theta is a function of time, is what we call theta 4, a function of time. So this is what we call the virtual, okay? This is virtual inertia. This is the way we usually express it. Okay, so this is mass. Okay, you see, this is force divided by gravity. So this is mass. Okay, see, we were insisting on that. And this is multiplied by the virtual radius of gyration. So this is the virtual radius of gyration. And usually we express it as a percentage of B. Okay, so we have B from here to here. Okay, so this value changes because in some cases you have several decks, right? So that means that you have mass away from the center of gravity. That means that it will increase the value of the inertia. Okay, so for example, typical values would be around 0.35 of B. Okay, if you have several decks or things like that, then you can expect a little bit larger value than that. But in that order are expected values for the gyration radius. Okay, now about the restoring moment, okay, this term here, this one here, we're going to assume that we are inside what we know as the initial stability region. That means that we consider that theta is small. For example, here, this is the problem that right now I'm facing. It's a fishing vessel called Yolinda. It's based in Manta. We're trying to help them with some stability issues. And these are the writing arm curves in 3 loading conditions. This orange curve, it's the condition when they depart from port. And in this case, in this condition, diesel tanks are full, water tanks are full, and also all the holds, okay, they are full with seawater right now. That's the way they come out from the port. And this gray curve corresponds to load condition number 4. And that means that when they return to port and all the holds are full of fish, but diesel is almost gone. So they assume that they're returning to port with only 10% of the consumables. So only 10% of diesel and 10% of fresh water. And in this case, the GM is much smaller than in this case, okay? So we're going to assume that we are going to be working in this area. So in this area, this is basically a straight line. Okay. So heel of rho, okay? In this case, theta is in radians, okay? So if you give this in meters, this in radians, the result is in meters, okay? So in the following analysis, GC will be replaced by GM theta, okay? Because we assume. It's something very interesting, right? When you do an inclining experiment, right? The classification societies ask you to move one weight a certain distance and measure how much is the inclination of the vessel, right? But this inclination cannot go further than 2 degrees. Why is that? I suspect that if you go beyond that, you start changing the trim. 2 degrees. That's what they allow you to move the ship. So that means that this region is really very small. But we're going to assume that even though we go up to 10 or 15 degrees in rho, we're going to assume that this relation holds. Okay, so GC is equal to GM times theta. Okay, so let's, in this class, let's go on and let's solve the free roll oscillation. Okay, so if we analyze this situation, then we will have no excitation. And we're going to assume that the damping is small. In that case, the natural frequency is going to be estimated only with restoring and inertial effects. No damping, and if it is free, then there is no excitation. So these are the equations that we are left with. This is virtual inertia. Now, instead of GZ, we have GM theta. So we're assuming that theta is small. And you see here that this term is constant. So we are limiting our analysis to a very small values of theta. Okay, and the solution for that, we know we could calculate the natural frequency like this one. Okay. And this virtual inertia, remember that we can express in terms of, so this J comma comma could be expressed as, this is mass, and then KXX squared. So we're going to have this in the denominator, which is going to cancel this delta. And this is the result. Okay. So GMT KXX double prime squared. Now here, instead of omega 0, you can express that as 2 pi divided by the period. This period, okay, it's something which is very important. Okay, for example, you could in one occasion I had to go to Galapagos for a vibration problem, and I was standing in the deck of the ship, and the ship was rolling. It was a very large ship, so it was easy for me to measure the roll period. It was about 11 seconds. So it's a nice parameter, because if you measure tau, right, you can have a rough idea of GMT if you make an estimation of the virtual radius of gyration. Okay, so this is what the IMO recommends to analyze the GMT in the case when you have small ship. Okay, when you have a small ship, right, and you do a inclining experiment, okay, in that case, the ship moves a lot. Okay, so it's very difficult to make a measurement with the pendulum. So in those cases, they allow you to, instead of moving the weight and measuring the deflection of the pendulum, instead of that, they allow you to get some people and move from one side, and when the ship is restoring, you ask them to move to the other side. So walk to the other side. Now, when it's restoring, you ask them, go to the other side, to the other side, to the other side. You can measure with the chronometer, you can measure the period. And using this expression, you can estimate the GMT. Okay, and in this case, for small ships, you can look up in the IMO regulations, and they gave you values for F, for C. Okay. Since I was looking at this stability problem of the Yolinda, that's the name of this ship. Okay, I looked up in the IMO weather criterion. Okay, this is the insect stability code. In the weather criterion, in some steps of the weather criterion, you have to estimate the period of oscillation. And this is the expression that they gave you for that. Okay, the period is 2C B divided by GM. So here, so you get the period, and basically that's something that you obtain. So 2C here is similar to this one here. Now they give you, in this weather criteria, they give you this expression to estimate the C coefficient. Depends on the ratio between the beam and the draft, and depends also on the water line length. Okay, so it's a very simple expression to evaluate. The GM is kind of difficult, and then at the end, you're going to have the period. Okay, I did this for this case of the Yolinda, and I'm going to show you these results. For you to have a general idea of the vessel, okay, from here to here, it's about 9 meters. And can you see that this is main deck? You have upper deck, and then you have some superstructure here. They have a mast with an observation point here. Okay, so you can see that if you have, for example, the center of gravity about here, right? Okay, you have a lot of mass away from here. This is my results. Okay, I consider the 3 loading conditions that they specify. Condition 2 is it has more weight and the GM is larger. Okay, this is the beam. I took it constant. The draft changes for each one of the conditions. The length is I took the same. And evaluating in the previous slide, this constant. This is what we have here. And finally, we have the period. Okay, so in this case, the GM is about 1 meter. In this case, the GM is about 0.38 meters. This is about 0.6 or something like that. So you decrease the GM and you increase the period. That means that it's like the ship, right? It gets lower. So you go on the one side and it takes longer to react. So it goes slower. So the GM, okay, is related with the period. So a very large period, that means that you have a low GM in general, right? So we have to be careful with that. Okay, and finally, this is something that I'm going to ask you to do in the homework. Okay, here it's something which is very useful. Okay, this is taken from Bhattacharya's book in chapter 4. Okay, these are typical values of the rolling period. Okay, in this case we have different type of ships, and these are the values of the ranges that you can expect to have the rolling period. Okay, in the case of a fishing vessel, we should expect values between 5.5 and 7. Okay, and if we obtain 11, that means that the GM in this case is very low. Okay, so they just say this, they don't say what type of fishing vessel is or anything like that. So as you see here, when you have a passenger ship, in this case, the period is very, very large. Okay, that means that in general, since the period is very large, the frequency is very low. And that means that the acceleration is very low. And that's it's a design requirement, because in that case, the acceleration doesn't affect much to the passengers and they don't get seasick. Okay. Okay. So those are typical values. It's a good idea to have in your memory. Okay. In what order of magnitude are these values, right? Especially if you apply stability calculations. Okay. As part of the process, you have to obtain the period in raw. Okay. So if you obtain I don't know, maybe 1 or 2 seconds of period, and you should review your results, because that's a very, an extremely low value of raw period. On the other side, for example, you have a 40, 50 meter long ship and you got 15 seconds in raw period. Hey, let me review, because it looks it's too high. Okay, so it's always a good idea to have these tables, right? So you can have a general idea what to expect. Okay, that's for today. That's it for today. As I said before, tonight, I'm going to start reviewing your quizzes, and hopefully for next Thursday they will be back to you. Okay. Did you all complete the solution of the quiz, people? Did you all have the? Good. On next week, next Thursday, not originally, I thought I would do it this Thursday, but there's no time. Next Thursday, not this one, in 10 days, okay? I will ask you to come to the university, those who can, and we're gonna do a test, simple test. Okay, we're gonna sit a simplified model in our wave tank, okay? And we're going to generate waves, so the model will roll. What we're going to do is we're going to change the frequency of the waves. So hopefully we will be able to identify the resonance situation, okay? Before that, we can do a very simple inclining test. So we will have an idea of the GM. We can do a simple test, decaying test. So we can apply logarithmic decrement in order to determine the damping, and that's it. And let's see what you will obtain, and then you will have to do the calculations, and hopefully they will be at least close. Okay, people. I want you to be aware that we need you to tell me what are the dimensions of the project, okay? So each group will have to send to Giovanna, okay, a short description of your vessel, okay? For those of you who are not taking ship design, okay, I'm really worried about them because they have their design. That's the ship that you're going to analyze. Those of you who are not taking ship design, please, I need you to tell me what is your ship that you're going to analyze. Okay, is there any question, people? Any questions about anything? No?
I have a question.
Yeah,
the
go
route
on.
that we right now for the lab sessions is the same route for the project?
Yes.
Okay.
Yes. Yes, definitely, yes. Okay. And for the test on next week, it's not necessary that each one of the members of the team come, right? Because I understand some of you live outside Guayaquil. So what we do is at least, hopefully at least one person in each group will come. So you will see what you're doing, you will get the information and will bring it to your teams, and you will later on you will be able to analyze it. And the idea is that each group can make a different load condition. And at the end, we can put the loading conditions one by side and we will see if that makes sense or not. That's the general idea. Any more questions? Any other question, people?
Doctor, I have a question.
Yeah, go on.
There are a limit of the length of the ship, a limit length or not?
No. If the ship is too small, right, it give us some problems because usually what we try to do is we evaluate the response in irregular waves. Okay, that's the last part of the semester. And the problem is that after you calculate, for example, the RMS value, that probably you remember that from the statistics class, right? RMS, root mean squared. You calculate that, and then what do? We compare with some standards. But if the ship is too small, usually it's difficult to find any standard. So at the end, is this good or is this bad? And we cannot answer that because sometimes it's difficult to find a standard to compare. So it is too small. I prefer that you pick a larger ship.
Okay, doctor, thank you.
If you have problems, what we can do is, if there is any group here that doesn't have a ship, I can give you the Yolinda. And I have, supposedly we have the whole thing and all of that. And we can do it, these things, and then with, I don't know, at least that would be nice. So if any group doesn't have a ship to analyze, I can give you the Yolinda. And we have some information here. we have to be careful because it's a real ship, it's a real owner and all of that. So yeah, we cannot just share all of this with outside. But yeah, we can do it. We're gonna change her name, okay? Instead of Jolinda, it's gonna be Jofea. And nobody will recognize that. Is there any group that the 3 members are not taking ship design? Question? People? Any group does not have at least 1 person who is taking ship design? No? Misayo, in what group are you in?
I am in the group, I don't know, 3, I believe, is with Barba and Zamora.
Are they taking ship design?
No, but we take the metallic construcciones metálicas. So we have a ship, but each one of us have a different ship.
Okay, you can take mine if you want.
Yeah, I consult with my partners.
Because it's realistic.
Yeah.
It's not an invention. We have the loading and we have all these things. Yeah, we could go on and try to input this in Rhino and all of that. But we have all these values. Okay, people. Any other group who doesn't have any person, any student in the ship design class? Every other group has at least 1 person in ship design? Yes? Okay, so that's my proposal, Misayo. Talk to me. Everybody has to send a short description of your ship to Miss Kinder, okay?
Excuse me, doctor, when do we have to send this information?
As soon as, I mean, if you are in ship design, you know, you have all of this information, right? So it's just a matter of sending, for example, what type of ship, what are the loading conditions that you have to consider? Probably you have already talked to that with Engineer Dominguez. And who are we know what the members are in this group. So that's it, or the main dimensions.
Okay.
Yep, that's it. So that's simple. But I would like to receive it as soon as I can. Okay, so for example, next Thursday, I would like to know how are we going to have these final projects. Okay, people, I'll see you Thursday, okay? Remember, next Thursday, in 10 days, I would like you to come to the university to do the test. I know.
Thanks, doctor. Have a nice.
You too.
Thank you, doctor.